second seminar organized by the RIOT Norway team. With me, I have my colleagues Anders Nordahl Hansen and Agata Puczynska. Agata has joined us recently. She currently works on implementing and teaching open and reproducible research practices at the University of Oslo. Now, just a few things about the RIOT Science Club for those of you who are not yet familiar with it. The RIOT Science Club is a self-organizing initiative. We host weekly seminars that aim to provide training in reproducible, interpretable, open, and transparent science. All our events are free and open to anyone. If you cannot make a particular event or would like to keep track of upcoming events, please check out our website, Twitter, OSF, and YouTube channel. And you can also join our mailing list. So you can find all these links in the chat in a minute. And now Agata will say a few words about housekeeping. Take it away, Agata.
Thanks so much, Tamara, and thanks for the introduction. Welcome, everybody. Just a couple of words about some practicalities. You can ask your questions in the Q&A message board. I'm sure some of you are already familiar with that. If you're not, you will see on the bottom of your Zoom Q&A. So please post your questions there during the talk. We'll try to get to as many as possible during our Q&A at the end of the talk. The questions will be moderated by me, Anders, and Tamara. So we'll try to do a good job about that. And now to introducing our guest speaker today. Take it away, Anders.
Yes, it's a great pleasure to invite or to introduce Dan Quintana. That will have the talk called 5 Things About Open Science That Every Researcher Should Know. A little bit about Dan. He's a senior researcher in psychoneuroendocrinology at the University of Oslo. His research investigates how hormones influence our thoughts and behaviors, and the neurobiology of autism spectrum disorders, and research methodology as well. Along with his research, Dan is also a science communicator, using various social media platforms and podcasts to share scientific research and discuss the scientific research process. He took his bachelor and the PhD in Sydney and later moved to Norway, currently residing in Moss, I think. Beautiful small city here. Over to this talk, he will talk about 5 things about open science that every researcher should know, including how open science practices can benefit both your career and scientific discovery. He will also provide some practical tips on getting started with open science practices as well. So I give the word over to you, Dan.
Great. Thank you for the introduction, and thanks for the invitation to speak, Anders, Agata, and Tamara. I'm really excited to share this presentation. Let's just get started here. There we go. So yes, I'm going to be sharing 5 things that about open science that every researcher should know. But to give a bit of context about how I actually got interested in open science, I'm just going to give a bit of a background about my work and what led me here. So I primarily work with oxytocin, which is both a hormone and a neuromodulator. Oxytocin is produced mainly in the hypothalamus, and it's released in the brain and also released within the body, and influences a number of physiological processes such as appetite, for instance, and metabolism, but it also plays an important role in behavior as well. And there's been a lot of interest in oxytocin's role in behavior, which emerged about 20 years ago. And that's what I focused on a lot in my PhD. And that is what my research is focusing on now. But like a lot of areas of research or a lot of areas of technology, oxytocin has gone through what's been called the hype cycle, in which there was initially a lot of research going, hey, there's a lot of potential for this particular hormone for the treatment of psychiatric illness, or more specifically for the treatment of psychiatric illnesses characterized by social dysfunction and by repetitive behaviors. So there's a lot of work looking into this, and then that led to a whole bunch of hype, and everyone thought this is the wonder drug. This is what we should be giving to everyone. We should put it in the water. We should spray it in the air conditioning vent so everyone gets a whiff of oxytocin. It even got to the point where people thought we could even prevent wars by giving oxytocin to everyone. Things were getting pretty crazy. But then we got to the point where there was a lot of disillusionment with oxytocin's effects. People started reporting non-significant results. People weren't able to replicate these original findings. The most famous finding to come out was in 2005, which was published in Science, which reported that a single sniff of oxytocin was able to increase trusting behaviors. And this is what really got everything on the map, and everyone got very, very interested in this. But since then, there's been a lot of attempts to replicate this using far larger sample sizes, and haven't been able to replicate this finding. So this is just one example of a lot of areas in which oxytocin has come under a lot of disillusionment. And of course, I started my PhD around this time. But fortunately, we've been getting into a period of so-called enlightenment, where we're getting a better understanding of what oxytocin does, and we're improving our research methods. And like I said before, I got into my PhD at around the time the findings were a little bit tricky to replicate. And that's what got me interested in open science and reproducibility in the first place. I thought this is such a fascinating area of study, yet at the same time, these results are not trustworthy and these results are not reproducible. So I began to get involved and learning more about how we could actually use open science practices and how we could actually improve reproducibility, so we can get a better understanding of what oxytocin does. And at least within my career and with other people who have begun adopting open science practices within their oxytocin work, this is beginning to pay dividends. Now we're getting more reproducible results, and we're getting a better idea of what oxytocin does. But look, this is not limited to oxytocin research. This goes across almost every single research field within biobehavioral sciences. This is an illustration of what things are like within psychology in general. This is an adaptation of a funnel plot, which you often see in meta-analysis papers. The dark circles are the studies that you see that are published. Now with the forest plot, what a forest plot does is it plots effect size against the measure of variance. And once you have those two bits of information, you can also calculate statistical significance. And that goes along this slanted line. And what you're able to do is you're able to visualize certain areas of statistical significance. So here we can actually see the statistical significance thresholds of 0.05, which is what we typically use, and 0.1. Looking at this particular area of research within psychology, almost every single study magically fell across this line. But all of a sudden, once replication studies started happening within this research field, they all fell around 0. So that is one demonstration of what replication studies and what open science can do in terms of improving the trustworthiness of results. But we're going to get back to that a little bit more. Okay, the first thing that every researcher should know about open science is that open science helps accelerate the scientific progress. So we're going to get a little bit into the philosophy of science here, but I think it's important to understand the value of open science and of pre-registration and of reproducibility, is to think about what is our philosophy of science? How do we approach research questions, and how do we actually go about scientific progress? I mean, this is a question, how do we build scientific knowledge, is a question that philosophers of science have been asking for a very, very long time. And I love this quote from Henry Poincare, which says, "Science is built up of facts as a house is built up of stones, but an accumulation of facts is no more a science than a heap of stones, a house." I think that's really profound. And that's one way of looking at how we can actually build that. But a lot of people have thought about, okay, so how do we get this plan, this structure of actually building this house of what we call science or scientific theories? One really compelling theory, I think, is the error statistical philosophy, which is from Deborah Mayo. And there's a fantastic book, and she's got a fantastic set of articles that I really encourage you to read. But essentially, this house plan is based on claims that have passed a severe test. And what a severe test is, these are tests that are easy to falsify. So this comes back to this sort of falsificationist idea, but this error statistical philosophy is based on these claims that pass a severe test. So here we've visualized a typical test within psychology or within most areas of the biomedical sciences. We have a null hypothesis significance test. So this is a two-sided prediction. So you may make the prediction that oxytocin administration there's going to be a difference between two groups, between oxytocin and placebo. There's going to be a difference. That's all we're saying. So this is your typical null hypothesis significance test. So we have a null hypothesis and we have predictions on both sides. Next, we have something which is, it's a bit, in terms of falsifications, a little bit different. It's a little bit riskier. You have a one-sided null hypothesis significance test. So rather than saying there is going to be a difference between oxytocin and placebo, here you would actually make a prediction going oxytocin will improve social functioning compared to placebo. So it's, instead of actually going across positive and negative, we're only going across positive there. Then we have something which is really, really risky, and this is range prediction. So rather than saying it's going to be positive or negative, you actually make a prediction and actually saying how much this difference between, for example, oxytocin and placebo is going to be. So you can see that there are different ways, or there's a different amount of riskiness for these particular tests. So if I was reading a paper and it actually said, we predicted this, that it would fall between this range, and it did, I would be very, very impressed, much more impressed than if it was a traditional null hypothesis significance test. There are a number of things that can reduce the capability of tests to be falsified. One of them is hypothesizing after the results are known, which is commonly known as harking. It's impossible to falsify that because you've looked at the data, you've seen what the results are, and you're pretending that that's what you hypothesized. So that's a really poor way of doing it. Another problem is hypotheses that are too broad. So an example of a broad hypothesis is something like oxytocin will improve social functioning. That's really broad. That could be, you can measure social functioning hundreds of different ways. You may do you may have actually measured those hundreds of different ways of improving social function. And by chance, one of those is probably going to work. And then you can say, hey, look, it improves social functioning. So by having really broad hypotheses, it's quite difficult to falsify. Next, we have data peaking, where essentially you run your analysis, and after every 5 participants, at least within a null hypothesis significance testing p-value framework, you test every 5 people. You can't do that. If you do that in the long run, you are bound to find a significant result anyway. And we also have analytical flexibility. So there are so many ways that we can analyze a data set. There are things to think about, like how do you deal with outliers? What kind of statistical test do you do? There are even small variants of each statistical test. And what variables do you use as an outcome measure? To give an example of analytical flexibility, there was a study that came out a few years ago which asked the question, do hurricanes with female names, because hurricanes, I think this has actually changed now, but historically hurricanes were given a name, and I think they switched between males and females. Do they cause more deaths because they're perceived to be less threatening? So the idea is, there's Hurricane Maria is approaching. Well, maybe it's not as threatening. Researchers hypothesized this, or in the paper, they said they hypothesized this, and they reported that yes, hurricanes with female names have less deaths because they thought that people actually thought, well, it's not going to be as threatening. But of course, with this particular analysis, because it's weather data and because the data in regards to deaths is very open, the original analysts were able to analyze the data, but it also meant that other people could come in and analyze the same data as well. There's a fantastic type of analysis called multiverse analysis, where the concept of multiverse analysis is you think about the entire universe of analyses that you can potentially do in terms of how do you deal with outliers, statistics, and all that kind of stuff. And so for this particular research question, these researchers looked at 1,728 possible analyses, looking at this exact research question using the same data that was used in the original data set. And although most of these analyses actually came to the conclusion that yes, these female named hurricanes have more deaths, the effects were tiny, almost like you can attribute it to chance. And of all these particular analyses, very, very few, I think it was less than 1%, actually had a significant result. So that shows you that you have an entire universe of potential analyses that you can do, and that gives you a whole bunch of flexibility. Yet if the researchers at the very beginning actually specified, okay, this is how we're going to deal with outliers, this is our enact analysis, and they found what they proposed originally, then you're going to get really impressed. So that's this whole idea of severe tests. How risky is this particular test? Thinking about pre-registration, or the main goal of pre-registration, if you adhere to this sort of error statistics philosophy, which I think a lot of us do without thinking, but a lot of us, I think more and more of us should formally, because it makes a lot of sense, is that pre-registration allows others to transparently determine the severity of a test. So when you're reading a paper and you can look at this pre-registration where people actually specified before they collected the data, this is what they're going to do, you can actually see, wow, this hypothesis was really broad, or this hypothesis was super specific. I've reviewed some particular papers with the pre-registration where they actually simulated the data from scratch and actually proposed, this is the exact code I'm going to use for my analysis. And then later, then you can actually see, yes, this is the code that they used. And I was very, very impressed because I was able to see they were so specific and so sure about the code they were going to use and how they're going to do it with outliers that they proposed it beforehand. So that worked really, really well. So for me and for a lot of people, this is what the purpose of pre-registration is, to transparently determine the severity or how risky a particular test is. Okay, so now for the second point, and that is sometimes you're not ready for hypothesis testing. I remember a couple of years ago, but back when we actually traveled before Corona, I traveled to Netherlands to visit a few labs, and I visited one lab, the Daniel Larkins' lab in Eindhoven, and Anne Scheel was doing a talk as part of the lab, and it had a really provocative title that when I first heard it, I thought, that's incorrect. I really wanted to listen to what she had to say. And essentially what she was saying is, you know what, we should be doing less hypothesis tests. But when she actually went through the talk and explained what she was talking about, I thought that makes a lot of sense. And that talk ended up becoming this paper here, which is why hypothesis testers should spend less time testing hypotheses. And I think you should read it because it makes a lot of excellent points. But there's this idea, and look, I talk to a lot of junior researchers and they say, how do I do a pre-registration? I'm like, well, what do you predict? And they're like, well, I don't know. I think there's going to be an effect, but they can't really say much more than that. And if you don't know that much, or if you're not really sure what to predict for your test, then perhaps you're not ready for an hypothesis test. And the thing about open science and reproducibility is, unfortunately, at least in some quarters, there's been a sort of, I'm not sure, this definitely has, I don't think this has been intentional, but in the sense that hypothesis tests have been elevated compared to exploratory research. I think they're both extremely valuable. When it comes to forming theories, we need to have these exploratory tests in order for us to actually come up with theories. So exploratory research is just as important as hypothesis-driven research. But in order to get to the point where we're doing hypothesis-driven research, we actually need to get a little bit more information before we make those hypotheses. And a lot of the reason why we're not actually getting reproducible results is because our theory isn't strong in the first place. This paper inspired me so much that I actually wrote a paper inspired by this, and in the context of oxytocin research, which asked the question, okay, are we ready in certain areas of oxytocin research? Are we actually ready to make hypotheses or to put together hypotheses? And what do we need to do in order to get to that space? And the basic idea here was that you need what's called a strong derivation chain in order for robust hypothesis testing. You need strong methods, because if you're not asking the right questions in the first place, no wonder you're not getting effects. You need these, and these theories build onto experimental models, which are your hypotheses, which build onto your data models, which is your analysis, and then you get to your scientific claims. But your scientific claims can only be robust if these other levels are strong. So If you're not sure about your hypotheses, and if you think, well, there might be an effect, there might not be effect, then perhaps you're not ready for hypothesis testing in the first place. So a lot of people might get the impression that when it comes to open science and reproducibility, that you need to pre-register everything. Everything must be pre-registered. It's just not the case. I've seen a lot of cases of people talking where they got reviews back going, well, this is an interesting exploratory question, but you didn't pre-register anything. And it's like, of course, it's an exploratory it's an exploratory question. It's okay to run these exploratory tests because we need that in order to build theories. We need these exploratory investigations in order to better understand our experimental models and just to better understand the questions that we're asking. So exploratory research is just as important as hypothesis-driven research, and you don't always have to test hypotheses. And look, we need these three things. A lot of people think, oh, you know, we can, for a long time, the thought was the way we can improve reproducibility is by having these reproducible methods or by focusing on theory methods. And more recently, people have been talking about the importance of theory, but I think we need all three in order to move research fields forward. So it's important to focus on all these three things. Okay, the next thing that I think every researcher should know about open science is that your future self will thank you for adopting open science practices. You're going to save time. You're going to save time in the long run. I'm not going to pretend that learning these practices is not going to take time itself, but it is a very, very important investment for your time. Because look, after peer review, you're invariably going to have to change or adjust your analyses based on what a reviewer has to say. But if you did your analysis from scratch, and it can take a lot of time to recreate that, but if you're adopting open and reproducible practices, and you've either saved your analysis as a script in R, or you've saved your analysis in Jamovi or JASP, or if you're using SPSS and using SPSS syntax, then it is a much easier way to reproduce your analysis. So your future self will thank you. About, years and years ago, that's how I did things. I'll do an analysis and I'll just rely on what I wrote in the paper. But now it's much, much easier because all my analysis is set in R, and it's very easy to recreate the sort of analysis that I'm doing. And yes, your past self does not return emails ever. The amount of times, at least in the past, where I'm like, how did I get this result? And it would take me a long, long time to actually figure out what I did to reproduce what I did. By doing that, you are giving your future self a favor. It is important to recognize that open science and reproducible practices, it doesn't take longer time in total. It just redistributes where you are spending your time. So rather than actually spending your time redoing your analyses and trying to figure out what you did afterwards, after you've done or submitted your paper, you're simply moving where you're spending your time a little bit earlier. So I think it's important to remember that, especially it can be a little bit frustrating thinking, oh, do I have to comment my code? Do I have to do all this stuff? But if you're doing this stuff earlier, you are saving time in the long run. The fourth thing that every researcher should know about open science practices is that you don't need to adapt all these practices at once. There's a whole lot of stuff to learn in terms of transparent code, pre-registration, preprints, all that kind of stuff. There's a lot of stuff to do, but you don't have to do it all at once. It isn't all or nothing. And I would recommend to start applying these practices just paper by paper. Learn one of these tools. Learn how to share an R script. Learn how to use OSF, Open Science Framework, for your research. Every time, every single paper, it gets a little bit easier. And the thing is, it's difficult, but because it's difficult, that means that open science tools are valued because they take time to develop. This is a spreadsheet, which I think it's taken a while ago, so it's a lot bigger now. But this is a spreadsheet of academic jobs that specifically say that open science practices are an advantage. And this is happening more and more. An increasing amount of these job announcements indicate that open science practices is an advantage. So this is really good for your career because it is a difficult yet valuable skill. And on top of that, a growing number of journals also require reproducible methods as well. So if you're going to be submitting to these journals, rather than learning it at the point of submission and it's almost too late, you need to be learning this stuff now. You can't pre-register a study after you've collected the data. It can take a long time to introduce this into your lab. And I love that that saying that the best time to plant a tree was 20 years ago or today. And that's exactly the same thing with open science practices. You might think, oh, it's too late, but just start today when it comes to learning these things. And the final thing that every researcher should know about open science is that it increases the speed of feedback. And personally, this is my favorite thing about open science and reproducibility and transparency, is that it increases the speed of feedback of your work. We all know the traditional publication system, in that you submit your paper to a journal, it'll take a few weeks for the editor to read it, and maybe they decide to send it out for review. That process can take a couple of months. And then finally the paper gets back to you. And this might happen twice, this might happen 3 times. And look, this entire process, if you're lucky, can take maybe 6 months to a year. If you're in the humanities, this can take 2 years. It is a very, very long process until the world gets to see your paper, until the world gets to see your work. And at this point, the only people that have seen your paper is you, your collaborators, and the peer reviewers. And the only feedback you can get is from your collaborators and from your reviewers, and maybe the editor as well. But with open science, you can actually provide and give instant access to anyone to see. So by posting your paper on a preprint server, by posting your code on Open Science Framework, for instance, and by posting all that stuff, people can give instant feedback on your work without waiting for that 3 months or 6 months or a year to get feedback from a small group of scientists. With open science, you can actually post your paper and people can go through your code or go through your scripts and provide that feedback. And they might say that, yes, you're wrong, you need to change these things. And these kind of opportunities, you just don't get with the traditional way of doing science. With open science, with open code, with open scripts, with preprints, you open up that opportunity to get fast feedback on your work. So I want to give a bit of a digression and a story of a paper that I published a number of years ago, just when I was beginning to kind of get into open science and begin adopting these practices. I wrote this paper, which was a guide on doing a Bayesian inference for or Bayesian alternatives to common null hypothesis significance tests. And I thought, oh, this is great. I'm going to post a preprint. I'm going to try and get some feedback. I'm going to post my analysis scripts online so people can actually go through and see that. People are going to say, yeah, this is great. Make a few changes and away you go. But I posted it and people found a lot of mistakes in my paper. Nothing huge, but enough that I needed to change things. So I went back and I was able to make changes based on the feedback that I got, which I never would have gotten, or I was highly unlikely to have gotten through peer reviewers, because again, the audience was essentially unlimited. A lot of people actually read through the paper and got a lot of feedback from people on how I can improve the paper, some misunderstandings, some bits that weren't clear. People went through my scripts and said, I think you should change this. I think you should change that. I think you've overinterpreted that. And that's just the kind of feedback that I probably wouldn't have gotten with peer reviewers, and the peer review itself took a long time. Yet that feedback that I got was almost instant. So this is a great example. And essentially what happened was the original co-author that I worked with for this paper, he went off to industry and just didn't have the time to work on the paper. But one of the people that provided the critiques in that paper, he gave some fantastic critiques, and I asked him, hey, do you want to join me as a co-author? And he did. So I was able to find a co-author, all because all this stuff was public and transparent. The preprint was out there, the data was out there, and I put myself out there to kind of go, hey, can you improve this paper? So that's one particular benefit of having open science and these reproducible practices. So how do you actually get started with doing these practices? I think it's important to start early, to start as early as you can, or to start now if you haven't already, because this is a key skill in science. And look, I think I get a lot of questions from PhD students and from master students going, oh, I'm not sure how to do it. My supervisor really isn't into this. I would just start documenting your analysis and just make this part of your manuscript. Of course, you need to work closely with your supervisor, but I think there's a lot of benefits. And as long as you actually speak to your supervisor going, hey, most papers, most journals are totally fine with preprints, and pre-registration when relevant is encouraged. and just presenting the facts. And it's a great way to, or just demonstrating how it all works is a great way to show to your supervisors and people that you work with that these practices can actually benefit papers. I mean, there's a huge open science community online, mostly on Twitter, where you can get a whole bunch of resources. We have these fantastic clubs now, like RIOTs, where you can actually learn about open science and reproducibility. But social media is a fantastic way, particularly Twitter, to learn about these open science practices. For me personally, for my career, like I don't think I'd still be a scientist if it wasn't for Twitter. I started really using it when I was in my postdoc, and that's how I learned about all these new techniques. It's how I learned about open science. That's how I built collaborations with people who are much smarter than me in order so I could pick up these practices. But it only happened because I was meeting them over Twitter. So for your scientific career, I really recommend learning more about it and how it can work. And it was so good for me that I just decided to write a free book. It's a very, very small book that I think you could read in a very short sitting. But this goes through how you can use Twitter for your scientific career from beginner to advanced levels. So even if you've been using it for a while, maybe you can get some new tips in the advanced levels. And there's even a 1-month boot camp at the end where I offer some suggestions on stuff to tweet if you're a bit lost on the stuff that you can talk about. And so if you want to learn about open science, I really encourage you to get involved on Twitter and get involved on the open science community on Twitter as well. Now, the gold standard of reproducible hypothesis-driven science is the registered report. Now, this is a relatively new way of submitting scientific articles. I think up to 300 journals now, maybe even more, accept registered reports. And this is great. Like I remember learning this. This is the science that I learned in high school, in that you make a hypothesis and you test your hypothesis, and then you actually see did it actually match, or was it actually consistent? Because there was a long while that science was not going down that path. But with the registered report model, essentially your proposal or your manuscripts are assessed in 2 stages. And in the first stage, your proposal is assessed just with the rationale and just with the analysis. So with this particular model, the reviewers can actually see, okay, how risky are these predictions? You can actually see if the hypotheses are too broad, and then as a reviewer, you would go, your hypotheses are too broad. And then you can give that feedback. And then if they make it to stage 2, then the papers are going to be published regardless of the results, which I think is critical for science. Yeah, it's a fantastic way of doing hypothesis-driven research. And for me as a reviewer, they're my favorite papers to review, because I'm actually able to, you can't change an experiment that's already been run. It's very difficult to actually say, well, you should have done this because it's already happened in the past. But with a registered report, you can propose changes to the experimental design before the data collection actually happens. And what happens is the reviewers at the second stage actually check, did the authors do what they say they were going to do? Did they, how precise their hypotheses? Did they do the test that they said they were going to do? It's a fantastic model. The funny thing about registered reports is they make null findings magically appear. So when you actually look at registered reports versus comparable traditional results, the percentage of null findings for registered reports are much, much higher. So it's a really stark demonstration of the difference between registered reports and traditional scientific papers. As well as significance and non-significance, registered reports also have this magical power of shrinking effect sizes. So this is a wonderful plot written, published in a paper published in 2019, which contrasts papers with pre-registration and without pre-registration. And the papers that were pre-registered tend to have smaller effect size. So this is interesting in the context of meta-analysis, because meta-analysis often takes effect sizes from articles that are not pre-registered, and these effect sizes are likely to be largely inflated. And people also use these articles for doing power analysis. And that's another reason why you should not use, or you should, when possible, avoid using prior research as a way of determining your effect size, because published effects, especially if they're not pre-registered, tend to be inflated compared to their true effect size. So that's another thing that pre-registration does, is it shrinks effect sizes. Look, many of you may have seen this this plot or this pyramid. It's this so-called hierarchy of evidence, where it compares case reports and animal trials, all the way up to meta-analyses. And it concludes that meta-analyses are the top of the evidence pyramid. I'm not sure this is particularly true anymore, or I don't necessarily believe in this. Whereas now, I think what's more impressive would be a meta-analysis of registered reports where you're actually collecting different effect sizes from registered reports. Like I showed before, effect sizes from studies that are not pre-registered tend to be quite large. So if there was a collection of studies, or if there was meta-analysis which synthesized a number of papers from registered reports, then you'd be quite confident that those effect sizes are truthful, or those effect sizes are robust. So this is a new model with the status quo research right at the bottom. And I think it's great that we're looking at ways that we can improve our research. And when it comes to hypothesis-driven research, which is what a lot of us do, the registered reports model is a fantastic way of doing that. So yes, I'm going to close up because I really want to spend some time doing some Q&A and speaking with you all about questions that you have about open science and reproducibility. But before we finish up, I do want to thank my research funders. And both these funders are very, very supportive of open science. So very appreciative both to the Research Council and the Kavli Trust. And yeah, we're going to keep chatting, but let's stay connected. And I'm also going to post, I've posted the link to these slides as well, which I'll add to the chat while we're doing the Q&A. So yes, thank you for your attention, and let's have a good discussion.
Thanks, Dan. It was really lovely talk, and I really love the practical approach to open science, because I think that what we often do is that we speak about how good open science is, but how to get started. It's maybe we don't talk that much about it, and it's so important. So thanks for your lovely talk. And now it's time for questions.
All right, so we got a couple of questions in the Q&A. Please keep them coming. Any questions you might have, just type them in the Q&A box. There is one question about whether you can recommend a website that can help with finding and evaluating software that facilitates software for open reproducible methods, for example, SPSS syntax. I guess the question is about, is there some sort of resource where you can go and look for software that is, suitable for open and reproducible research? Do you know of any resource like that?
One might exist, but not one that I know of. I guess it's just a matter of looking at the software that's available. I mean, looking at published papers and seeing what people is using is one way of finding it. But for the example of SPSS syntax, yes, sharing your SPSS syntax is transparent because other people can reproduce it, but that's predicated on other people having an SPSS license, which a lot of people don't have. I haven't loaded up SPSS in a couple of years, and if someone came with an SPSS syntax, it would take me a long time to actually load that up again and file the license. So I mean, but SPSS is, as an example, isn't open. But if you're doing something like R or JASP or Jamovi, then that's something which is reproducible. So essentially, asking the question, can someone else for free run this analysis? And if the answer is yes, then that's a good solution. But as for an actual website, I'm not sure. So if anyone else has suggestions for that, add it to the chat, but I'm not sure about that.
Yeah, I'm also not familiar with one resource that would sort of gather all these resources, although I'm pretty sure that when you start reading up on open and reproducible science, and you start sort of looking for these simple tutorials on open and reproducible science, there will be different types of software mentioned there that, as Dan says, they're not only good for reproducible science, but they're also non-proprietary, so that they're open source, you can just use them free. So definitely connecting to the open science community on Twitter, for example, as Dan said, is a good way to learn about these things, and is a great resource. And also, Dan, I don't know if you mentioned that, but your Twitter for Scientists book is free online, right?
Yeah.
You can just read it free online.
That's
if
right.
you Google Twitter for scientists, I think you will get it up immediately.
Yes, yeah, I'll put the link in the chat as well.
Awesome. And then we have the next question that was actually my question to you too. So I'm really happy that more people are asking about that. The question is, do you think that there are benefits to pre-registering exploratory analysis? And to that question, I will add not only analysis, but also just pre-registering exploratory research in general. There can be I think some benefits to pre-registering, research questions, not specific hypotheses, but research questions that you have for exploratory research and the design and the methods that you will be using. What do you think? What do you think about that?
Yeah, I'm sort of along the same sort of thing. Like it's not as critical for hypothesis-driven research, and like I mentioned before, I think the main purpose of doing pre-registration for hypothesis-driven research is for transparently evaluating the severity or the riskiness of tests. But for doing this, I mean, it's good for sort of having a record of what you plan to do, but it's not as critical. So yeah. There are benefits, but nowhere near the same sort of benefits if you were doing a hypothesis-driven research.
I think some of the benefits here would be visibility of that research, right? Because of course, not every research gets published. If you pre-register your research questions, your methods, your design, it's out there. If you put it up on OSF, for example, an open science framework, it definitely increases the visibility and transparency of that research in case, especially if it doesn't end up being published, and especially if it's searchable right away. For example, it's not embargoed. And I think even OSF developed a whole template for exploratory, or is developing a whole template for exploratory research. So definitely there are people that are very for doing that, but there are some drawbacks too.
There's also a registered reports, exploratory reports template. I think one journal, Cortex, is doing it, and I think other journals are beginning to do it as well. But yeah, so it's there are benefits, but there are different benefits to why you would do it for hypothesis-driven research.
Right. And then the next question is, PhD students running lab experiments to test effects that are estimated from meta-analysis to be very small. Is it worth spending time on such experiments? Would require very large samples. Better to explore other areas of research with hopefully stronger, more robust effects? What do you think about that?
This is a great question. Very, very good question. There are two approaches here. You could formalize this. There's a lot of the effects that we have in psychology are very small anyway. So unless you're doing something in perception or psychophysics, you're going to need massive sample sizes or large sample sizes. And there's no point pretending that for students, we have a lot of resources to do these kind of experiments. There are platforms like CREP, for instance, where basically they propose common research questions that different groups can do and that students can contribute to. So although you may not have the statistical power to answer these questions, if you only have 20 or 30 participants, if you're doing a meta-analysis and there are 20 different groups working on this question, then you can contribute to that. So then it's worthwhile. So, and I think this question also comes to a question of resources for the student, but also what if you're working with a rare population? What if there's only 30 people within your region that have a disorder that you're working with? We can't just throw our hands up in the air going, we're not going to do research on this disorder because it's too hard. But if you feasibly think that a future meta-analysis can synthesize your data and other people can actually build on that, then it is worth it. Of course, you need to be very upfront in your paper going, people do all kinds of things to justify their sample size. But if you say, we're limited by resources and we expect this data to be used in the future as part of meta-analysis, then I think that's totally fine. So either join these networks like CREP, where you can actually join student experiments, which means that eventually you'll have the power to answer these questions, or be very upfront and say that we expect this to be used in future meta-analysis, which also means you need to be super transparent about your summary effect sizes. So it's very easy for other people to do meta-analyses, or even better, if you can, share your raw data, which makes it even better for synthesizing data sets. So yes, We can't just ignore certain questions because people have rare disorders, for instance, and we can still continue doing these and teaching our students how to do these experiments, even if we have low statistical power, by joining these larger networks.
Absolutely. Thanks so much, Dan. And we also get a follow-up question about, could we have a web link for CREP that you?
Yes,
that you
I can find that, or perhaps someone else can find that. But yeah, we can put that up.
Definitely. And we also got a resource that's sort of regarding the first question about open and reproducible practices and what kind of software would be best for that. The Turing Way is an online resource for learning about open and reproducible practices. And I'm pretty sure that some information can be found there. It's one of many, of course, different types of sort of web spaces for gathered resources like that, but it can be super useful for. So thanks so much to our participant for sending that over. And then the next question is, on what platforms do you recommend scientists to upload/register their code and data sets?
The two that come to mind would be Open Science Framework and Zenodo. There are plenty of databases and websites that actually have this feature, but the main things you have to think about is, firstly, are they going to be around for a long time? The websites like OSF and Zenodo have guarantees saying if we ran out of money tomorrow, we have enough maintenance and server space to keep our data hosted for 50 years or for 20 years. That's something that's really important to consider. And both Open Science Framework and Zenodo fulfill that. So those are important considerations. I know a lot of the journals even offer to host your code and scripts. And look, those are going to be around for a long time too. But I think it's very useful to begin building a portfolio of your analysis and scripts on something like Open Science Framework, because then someone, if you're going for a job and they're like, oh, do you, have you been applying open science practices? You can go, yeah, look at my OSF page, and you can go, here is my code, here is my scripts. And by having all that in one place, then I think that's a good way. But the most important thing is just considering how long will this be around for? Is this funded to stick around for a long time? Because the worst thing would be posting your code and someone reads your paper in 5 years' time and they can't find it. It's exactly the same problem. Data available upon request, yet the PhD student left academia 10 years ago. By putting your code on these websites, it's going to make it much easier for people to even yourself, to retrieve the data later.
Absolutely. Couldn't agree more. Data availability statements are really not the way to go anymore. And definitely can confirm from my part and from my field that OSF, Open Science Framework, and Zenodo are probably the most popular platforms to share your code and data sets. But of course, there are also these proper archives where people sit and curate your data over time. And that sort of gives a little bit more maybe security in terms of, this data will continue to sit there in many years' time. And Dan just posted the link to CREP. Thanks so much, Dan, for that. And then the next question that we have is, well, first of all, thank you for the talk, Dan, says the question. What is your opinion on the role of peer review and the adoption of non-hypothesis testing works? I find there is a fear in colleagues that papers that do not test hypotheses or just exploratory are disregarded by more old school peer reviewers who still always expect p-values.
Yeah, look, this can be a problem, and you can still report p-values but do exploratory work. But I find a lot of times, like, I've submitted papers and reviewers are like, "Where is your hypothesis?" And I'm like, I didn't have any. So I mean, personally, for me, I've actually gone through and explained, look, this was exploratory, and I tried to be as explicit as possible in the paper, saying this is an exploratory work. There were no hypotheses. So I think it just depends on research fields as well. Some research fields expect that. They expect there to be hypotheses, even though they weren't pre-registered. But I think this mentality is changing, and I'm not going to lie and say that some reviewers, every single reviewer is going to be okay with that. Some will expect these things, but you know, sometimes it's just about patiently explaining to the editor. If this was rejected because it was exploratory, then that's a problem with the journal. But these things are definitely going to happen. But I think it's important to actually explain within the paper why you're doing the exploratory analysis. Hey, we're trying to understand this phenomenon better. We're trying to help theory building, for instance. But look, it's going to happen. But I think the mentality is changing slowly, but it's changing.
Thanks so much, Dan. Keep posting your questions in the Q&A. We still have a few minutes. While we are waiting for more questions to come, I was thinking, Dan, of asking you, and you mentioned maybe something about that in your talk already, but what do you think is the easiest thing to start with? And I know that that's a very common question, and you're probably getting these questions. We are getting these questions very often. And you mentioned that just starting to document your analysis could be that sort of first step. You can easily just, you know, make good notes around the code or the different steps in analysis or the workflow. Do you think that's the sort of low threshold thing that every PhD or postdoc or professor can start with to start implementing open science practices, or would you choose something else or add something to that?
I think it's a really good start. People are already doing their analyses. So it's a matter of taking that extra step and documenting that. One thing that people are always afraid of as well is, oh, my code is too messy. My code is too messy. But I think as long as your code works, then I think that's okay. And it's very, very rare that someone's going to go, someone may go through going, I had trouble finding trouble following your code, but as long as your output actually matches what you had in your paper, then I think that's okay. If you're not comfortable with R, then you can begin sharing your work using JASP and Jamovi as well. I think Jamovi is great because it's got a syntax mode where you can actually share your Jamovi script as an R script, and you can share that as well, and it's going to reproduce the same sort of results. So I like thinking about doing ways you can actually just exploit things that you're already doing. You're already writing data. It's just a matter of sharing it. Same thing with preprints. You're already writing manuscripts. We know how much of a terrible experience it is submitting our manuscripts to journals, but submitting your manuscript as a preprint is super easy. It takes less than 10 minutes on OSF, for instance. You have to answer like 6 different questions and upload a few different things, but your preprint is up there. So preprinting your work, remember, the absolute majority of journals are totally okay with preprints. It's very rare that a journal explicitly says we do not accept papers that have been preprinted. So it is always worth checking that, but it's very rare that a paper does that. But preprinting your work that you're already doing, sharing the data and scripts you're already doing, that is probably the easiest and the first step you can do by adopting these practices.
Thanks, Dan. I have a question too. Could you say a few words about teaching open science? When do I think we should start? Whether we should start early on, yeah, and maybe about involving students into our projects, and so if you could say something about
yeah, I mean, I think it's important to start as early as possible. I speak to so many undergraduate students in psychology, and it turns out they've never heard of the replication crisis, and that blows my mind. It blows my mind that these ideas of replication and open science are not taught early on. Of course, you have to think about the level or the ability level and what students know, but there are ways you can actually introduce these within undergraduate courses. But once you start getting to master's levels and PhD levels, I think this should also be very critical, because it's a very critical tool that you have to use eventually in your career, and teaching these things early. I mean, coding in itself, even if you don't go into academia, is incredibly valuable. So these things should be taught as early as possible. And most people have taught themselves via the internet and online. Very few places actually have formal teaching on this is how you pre-register a study. This is how you share scripts. This is how you do analysis in R. So many schools are still teaching in SPSS. There's a whole bunch of stuff. So as early as possible, I think.
Thanks so much.
And then we have a couple more questions that came in the Q&A. One is, would you advise preprinting from the beginning of your PhD, your first article? My supervisors are a bit hesitant.
I mean, I think it's first figuring out why they're hesitant. Sometimes it's just they just have incorrect views in terms of, and that's not their fault. It's just what people know. And there used to be this old idea. I mean, everyone knows with journal articles, you cannot submit something which has already been submitted elsewhere. But what a lot of people don't actually realize is submitting a preprint article is the same as giving a talk at a conference. It's not considered sharing your work elsewhere. So first figure out what the actual, what they're worried about. And then once you figure out what they're worried about, then you can chat to them about that. But I would also talk to them about the benefits of preprinting. Articles that are preprinted get cited more. This is a fact. People have done a lot of analyses actually analyzing the citation patterns of articles that are preprinted versus not preprinted. Articles that are preprinted get cited more and they get feedback. So rather than actually talking to them about, or trying to allay their concerns about the dangers of preprinting, talk about the benefits of preprinting, about the feedback that you can get, and about the fact that they just get more citations, which I think most people will pay attention to. If you were told, here is a simple way to get your paper more citations, people are going to listen. So that's one way to do it.
That's a great point. And then we have another question about how can you be open and share analysis when data contains sensitive personal information?
This is a really good question, especially if you're working with clinical data or with rare disorders, for instance. There's one approach you can do is you can simulate your data. So if you want to share your analysis, you can still share your analysis without sharing your data. If you're sharing an R script, it may be more difficult to understand what's being done, but at least you can follow through the analysis to see what was done. The next thing that you can do is you can generate you can basically generate a data set which has the same characteristics of your original data. The output is going to be different. The results are going to be different, but at least people can actually go through and understand what you did. The third thing that you can do is create what's called a synthetic data set. And this data set actually has the same statistical properties as your original data set, the same averages, the same means, the same relationships between variables. And what that means is when you run the analysis, you're going to get results which are very, very close to the original analysis. So you get the benefits of reproducing your analysis and getting almost the same results while also maintaining participant privacy. I wrote a tutorial paper on how to do this using I can't believe I've got the name. I'll post a link to it anyway. But there's an R package, SynthPop. Yes, SynthPop. There's an R package where you can create synthetic data sets. And what it means is you can share your data, people can reproduce and explore your data, while at the same time you're maintaining the privacy of your participants. So it's difficult, but it's possible. But really the solution is don't think that your participants automatically don't want to share their data. Participants are more willing to share your data than you think. If at the very beginning of your research, you actually ask your participants, are you okay with me sharing anonymized data? I'm not going to share your name. I'm not going to share your age. In a lot of research, you don't even need age. I'm going to share your anonymized data. Most participants are like, yep, cool. I'll do that. If you can do that, then you're in the clear. But of course, it's very difficult to do that for data you've already collected. So in that case, then you could use the synthetic data approach because there's no way to identify participants, but you get the benefits of a data set that the others can reproduce.
Thanks so much, Dan. I think we're closing on the hour. Tamara, would you like to say a couple of final words?
Yeah, well, thank you so much for joining us, Dan, and thanks to all for coming today. And thank you to Oliver, who has been making all this possible for us. And this talk will be uploaded on our YouTube channel. And we also want to encourage you to check upcoming RIOT talks and on our website and Twitter, of course. So we'll see you again next time. Bye.
Thanks, everybody.
Thank you.